All right, so let's see if I can do this. This is problem 109, which is a common one that I saw people having issues with. So I'm just gonna let's go ahead and do this. So all right, basically got a free body diagram. So here we go. We got a mass. So here's the mass of block 1. Here's the mass of block 2. And then we also got a coefficient of friction right here. And what's the acceleration of the system? I think I'm going to assume that the acceleration of the system is going to go this way. I could be wrong, but I think that's what's going to happen. And one of the first things I want to do is tilt my axes, but also sync up my axes. So for mass 1 over here, I'm going to have an axis that does this. For mass 1, I'm going to have an axis that does this. And for mass 2, I'm going to have an axis that does this. Like this, yeah. Because the axes, again, I want the axes to go, so positive x is going to go all the way along here like this. So this is y and this is x right here. So downward is going to be x, is going to be the positive x direction for 2, for mass 2. So I've tilted my axes here, and let's just draw a free body diagram on mass 1 first, like this. So I would have, let's see, I would have the normal force, and I'm assuming, by the way, that the acceleration is going this way. I could be wrong, but the math should tell me later. So I would have a normal force like this, and I'm going to redraw all this. I'm going to have mg pointing down like this. I'm going to have a frictional force that's going to go against the direction of motion, and then I'm going to have a tension force that's going to point that way. So good, I think that's right. And then this free body diagram for mass 2 is going to be, there's a tension force pointing up, and then there's going to be the weight as well pointing down. But that's m2g, where this is going to be m1g. Let's see. So, and remember, positive direction is going to be this way. Is going to be this way, where the positive direction here is going to be this way. So let me really quickly, let's see. Mass 2 shouldn't be too bad, so let's start with mass 2 here. I got my free body diagram that's going to look like this, or let's do it over here. So my free body diagram for mass 2 is I've got the tension force going up like this, and I've got m2g going down like this, m2g like that, and the positive direction is down. So this is going to be F net, what? F net equals MA. So F net in this case is going to be mg, and that's m2g. m2g minus ft is equal to m2a. And I think that's about as far as I can get with that. So, and I'm going to call that equation 1. So I got one equation right there. Now I'm going to do M1, which is going to be a little trickier. Can I just copy? Let's see if I can just copy this over. Although I'm probably going to want to make it a little bit bigger. So I'm going to copy over my free body diagram here. Yeah, that's great. And then I'm going to make it a little bit bigger here. I think that should be good. The tension force should probably be a little bit bigger, but I'm not going to go with scale right now because I mean, well, yeah. I'm just going to stick with what I got here. So mg, it can be split into, so here's my angle, which is 37 degrees, right? And so mg can be split into m1g, that is. m1g can be split into its vertical component, so this is going to be mgy. And then it's also got a horizontal component across here, so this is going to be or here, I can do it here. So this is going to be mgx, and then my angle, 37 degrees theta. I'm going to try and do this algebraically. However, if it gets a little too messy, I'm just going to throw in numbers for simplicity's sake. So okay, I got mgx, and so something I can get out of here, you can do some trigonometry and get that mgx is equal to m1g. I should say m1. This is m2. Sorry, that's m1 as well. And please let me know if I make any mistakes or anything like that. So it's going to be mg. This is opposite. So it's going to be sine of theta, where for mgy, it's going to be m1g cosine theta. So I got those right there, so I'm going to plug those into my F net equals MA stuff. Let's see what I got here. So in here we got F net equals MA here. So in the vertical direction, I will have the normal force minus mgy, which is mg1 or m1g cosine theta, and that's going to equal 0 because my acceleration is 0 in the vertical direction. Again, remember I tilted my axes here. Okay, and then so I think then this just tells me the normal force is equal to m1g cosine theta, and that's about as far as I can get there. Okay, so there's equation 2. And let's see what x will tell me. So I have the tension force pointing to the right minus the friction force pointing to the left. And then I also got minus this mgx term over here as well. So it's going to be minus m1g sine theta is 0. So, okay, there we go. And so I can, you know what, I'm going to isolate ft, because I think what I'm going to want to do here is relate, I think I'm trying to find out the acceleration. Yeah, I'm trying to find out the acceleration. And the tension forces, right, this is what's nice about tension force, is that if this is a massless, if it's a massless rope and it's a massless frictionless pulley, which we can assume here, then the tension force between these two is going to be the same. So I'm going to find out what the tension force is and then plug in all that in there to get the acceleration. That's going to be my plan of attack here. So let's see here. So I'm going to isolate the tension force here. Let's go back to, here we go. So isolate the tension force. So it's going to be Ft equals force of kinetic friction plus m1g sine of theta. So I got theta, this is no problem. I got g, I know m1, but the friction force, now I got to get something to change that friction force right now. So, and typically where you go to change up your friction force, so here's equation 3, is that coefficient of friction approximation. So I'll say the force of friction is equal to the coefficient of kinetic friction, which they gave me, multiplied by the normal force. And then I could take this, I know what the normal force is, it's m1g cosine theta, so this is going to be ffk equals mu k times the normal force, which is m1g cosine theta. And now that I got that, so here is a fourth relationship that I've just found, 4, and what I'm going to do is I'm going to plug in equation 4 into equation 3. Right, I'm going to plug in equation 4 into equation 3. So in other words, all this stuff is going to turn into what FFK was. So that's going to give me the tension force is equal to, and instead of FFK, I now have mu k m1g cosine theta plus m1g sine theta. So there we go. I got all that. And I could factor out this m1g, but I think right now I'm just going to keep it as it is because I think I might, it might be. So here is now another relationship. It's relationship 5. And what I'm going to do now is plug in relationship 5, equation 5, into equation 1 because that's my tension force right there. So that's what I'm doing next. I'm going to plug in 5 into 1. And that's going to give me, 5 into 1 is going to give me, let's do it this. 5 into 1, so it's equation 5 into equation 1. That's going to be, so equation 1 is m2g minus all this stuff, so it's going to be mu k m1g cosine theta plus m1g sine theta equals my mass 1 or mass 2 times the acceleration. Let's see if I got that right. Oh, shoot. I screwed up here. Okay, sorry. My bad. I'm accelerating here. I'm accelerating here. So this is going to be mass times the acceleration along x. So it's m1a. My bad. My bad. So that's going to change. It's not going to change much, though, because that's just going to change this to plus m1a. So this is relationship 3. And that doesn't change. But this is now going to be, plus and one more term. So I got 1 term, 2 term, 3 terms here. Because right, it is accelerating in the x direction. It is accelerating in the x direction. We have an acceleration pointing this way in the x direction, and it's accelerating downward, right, as well. So I got that. Okay. So I think that's right now here. And this is equation 5. And then I'm now replacing all this. So this is going to be, I'm going to fix this to be plus m1a. And then this is going to be equals m2a. So let's double check here with this. So I got m2. This is all the tension force. And then this is m2a. Let's see. So m2g, tension force, m2a. And there is a minus sign in front of there. So I'm looking pretty good. Okay, so next up I want to be careful. I want to distribute this negative sign to all 3 of my terms here. So that's going to give me m2g minus mu k m1g cosine theta minus m1g sine theta minus m1a equals m2a. So now I'm going to add m1a to both sides. This cancels. And then I'll have m2a plus m1a. And I'm almost in the clear now. So I got m2g minus mu k m1g cosine theta minus m1g sine theta. Equals, this is going to be, I could factor out an a, so it's going to be m1 plus m2, factor out the a like that. So this is then just going to be m2g minus mu k m1g cosine theta minus m1g sine theta divided by m1 plus m2 times the and equals the acceleration. So once again, I've got, I've got, here is my F net, here's my F net terms up here, and then here's my inertia term down here. Because these masses is the inertia of the system, and then this is my net force. So here's the weight of M2, that's what causes it to accelerate that way. Here's the friction force term, that's what causes the opposite, is going against this weight term. Right, here's that friction force, and then here is the weight, the x component of the weight. This is the x component of the weight of block M1. So now all I need to do is just plug in all my numbers here. So what was M2 and M1? M1 was 4 kilograms, M2 is 8. So M2 is 8 kilograms. So we got, let's just plug in stuff here. So 8 times, I could factor out a g. Let's factor out the g. So I can factor out the g. It's going to be 10. So this is going to be 8 minus mu k. Oh, shoot. Mu k is 0.4. So 10, 0.4 multiplied by, g got factored out. M1 was 4. Please correct me if I'm wrong. M1 is 4. Cosine of, I think the angle was 37. Minus M1 again is 4. Multiplied by sine of 37. Let's see, is this all? That's not bad. All right. Divided by M1 plus M2, that's 4 plus 8. Yeah. 4 plus 8 equals the acceleration. Okay, so we're going to calculate exactly what that is. let's see. So this is going to be sine of 37 times 4. I got cosine of 37 times, times 4 times 0.4. All right, so I got 8 minus 3.59 basically, minus 2.4, and then all that multiplied by 10, and then divided by, so I'm getting all this multiplied by 10 on the top, I'm getting about 20 divided by 12 equals my acceleration, 1.67 meters per second squared. And I'm pretty sure that that's wrong. So what did I do? Because I think the answer is 3.6 something. So where did I screw up? Times 10. So now I got 43. This is actually 43.2. So that was just a miscalculation. This is actually 43.2 up top, divided by 12, and I get 3.6. That's correct. That's correct. So just a calculation error. Everything else was correct. Yay! So there you go. Definitely a fun one. Yeah. So hopefully that'll help you for your Atwood machine lab. All right. Thank you. Bye.